Today I'll be talking about two of my research projects, my previous work with molecular simulations of ice nucleation, and then my current in-process work looking at the spicule field campaign data set. And the background image is an ice crystal measured on the holodeck probe during spicule. So like Sarah said, I'm currently a PhD student at Michigan Tech, and my two amazing research advisors are Raymond Shaw and Will Cantrell. It's sort of a small, less known campus, so I wanted to share a photo of the campus. And some of the facilities in the cloud physics lab are a cloud chamber, where we can build a stable convective cloud cell and measure it. And we have a laboratory where we can measure droplets freezing on a cold stage with high-speed camera, and I'll show some of those experiments. And we have some high-performance computing clusters that I've used for my simulations. This is where Michigan Tech is located, on the Keweenaw Peninsula, sticking up into Lake Superior on Ojibwe homelands. And one fun meteorological event we get is the lake effect snow off Lake Superior. So we get these really fun winter activities, and this is a photo of Lake Superior in the winter. So I wanted to start by giving sort of a warning, like disclaimer, that the two topics I'll be presenting may seem very different in both topic and research approach, but they do become connected in the atmosphere. So I'm going to try to frame the talk through those connections. So the first research topic is regarding what are the fundamental physical mechanisms that determine what temperature water freezes at. And the second is what cloud properties influence the growth of the largest cloud droplets in developing cumulus. And I'll be discussing both of these topics mostly through the lens of thermodynamics. So to start, I want to introduce this topic, which is that cloud droplets larger than about 55 microns are needed to start the collision coalescence process in clouds in order to grow into larger droplets and raindrops. And how droplets reach that size isn't completely understood yet, because growing to that size through deposition of water vapor would take a really long time. So I'll be calling this the droplet growth bottleneck. Furthermore, large cloud droplets are linked to high ice concentrations in clouds. And for those of you who listened to Paul Lawson's talk a few seminars ago, he gave a lot of background information on these observations. But I put two quotes here from different observations of this phenomenon. So one from 2001, where the amount of ice is strongly dependent on the largest cloud droplets generated in the cloud. And a more recent one in 2011, Sarah Lance et al., where they found similar results for high ice particle concentrations correlated with droplets larger than 30 microns. Also, there's been some interesting ideas put forward about whether or not supercooled droplet collisions in the atmosphere might cause the droplets to freeze, or if the breakup of large droplets in the atmosphere, if they freeze while those droplets are breaking up. And so here's just some of the articles that have been published that have put forth this hypothesis. And these figures are both from the first paper, where these are in-situ samples that were collected of two frozen droplets that were stuck together, and they were frozen at the time that they were collected. But this is also from this Koenig 1965 paper, Drop Freezing Through Drop Breakup, discussing how violent motion has been thought to induce ice nucleation in water. And he refers to some experiments by Dorsey in 1948, which I've also read through. They're interesting. He has supercooled water and is just trying out different things to see which things cause it to freeze. And sometimes you can pour it from end to end in an ampule without crystallizing it, but if you violently shake it, then it freezes. And it seems like the more violent you shake the water, the more probable it is that the water will freeze. But he also mentions that why things like bubbles and cavitation would lead to freezing is not understood, and this is the case. There's still a big mystery around why mechanically agitating water would cause it to freeze. And so that's sort of this long-standing mystery around the super cold water bottle trick that is kind of fun to watch. So I'm going to start with this topic of why would collisions and breakup of big droplets cause ice nucleation. So first I'll give some background on ice nucleation theory. So we mostly understand ice nucleation through classical nucleation theory, where ice nucleation happens at a certain rate J, which is number of ice nucleation events per unit volume of the water per unit time at a given temperature. So it's formulated to be predominantly temperature dependent. And so here you see temperature in the equation, and there's also this delta mu term, which is the chemical potential difference between the ice and the water. Actually, I think I can turn on my computer. So here's a phase diagram, temperature versus pressure for water. And at the coexistence point between ice and water, along this black line, the chemical potential is equal for both ice and water. But the further you move away from the coexistence point, if you're lowering the temperature, but you're still in liquid form, the larger the difference between their chemical potentials become. And so this gets larger and drives higher nucleation rates. There's two types of ice nucleation. Homogeneous ice nucleation happens in a volume of pure water, and heterogeneous ice nucleation is when the ice nucleates on a third surface. And I think that is enough. That's all the background we'll need on ice nucleation to go forward with the experiments. So the first mysterious aspect of supercooled water was observed in this experiment in Raymond Shaw's lab in 2005, where if you have an ice nucleating particle positioned in the volume of the droplet versus positioning it right at the droplet surface, the nucleation rate at the surface will be many orders of magnitude greater than when the same ice nucleating particle is inside of the water droplet. So this might tell us that the surface of the droplet has a higher nucleation rate than within the volume of the droplet, or the surface at least plays some important role. However, though the droplet surface is clearly important, as shown in the previous experiment, it's not solely responsible for that experimental result. In 2011, Colin led this experiment to sort of verify the previous hypothesis. So the droplet is resting on an ice nucleating surface, but the substrate didn't have a higher nucleation rate at the surface of the droplet like we expected. This plot shows all the freezing locations, and there was no preference for the surface. So the surface has some role to play, but it's not the only factor here. So then in 2018, there's another experiment from Raymond Shaw's lab that gives another hint, which is that if you have a droplet on your substrate, and in this case the droplet's moving up and down, being spread up and down on the surface, which I'll show some videos of. If the droplet surface is perfectly smooth, and at -17°C, the droplet will never freeze during the time it's observed. However, if you have the same volume of water on the same substrate at the same temperature, but you modify the experiment so the droplet surface is curved and wobbly and stretched, this droplet will freeze within a fraction of a second. So the curvature of the droplet surface caused a higher nucleation rate. Oh, sorry, I went the wrong way. So going back to that first experiment, one might speculate that maybe what's going on with the ice nucleating particle at the droplet surface could be something like this, where there's some small-scale curvature of the droplet surface where the ion is touching. But this is, of course, just speculation. It's a hypothesis. In summary, the experiments, this is another one in 2015, show that some processes can increase the nucleation rate of the ice nucleating substrate without lowering the temperature. And the trend seems to be that the droplet surface is curved and stretched, and the ice nucleation takes place at the droplet's surface. So, as I explained before, classical nucleation theory formulates the nucleation rate to be temperature dependent. But if there's some mechanisms that can increase the nucleation rate without changing the temperature, there must be some other variables that go into the nucleation rate. So our hypothesis is that pressure could be another variable that influences the nucleation rate. So in order to add a pressure dependence to the nucleation rate, we use a pressure-dependent formulation of the chemical potential difference, which was derived by Nemec. So the added term is a change in pressure relative to 1 atmosphere, or the reference pressure. And this is the molar volume difference between liquid and ice. And since ice is less dense than water, this delta VLS term is negative, which means that if we wanted to increase the nucleation rate, we actually would need a negative pressure. So now I need to clarify what is a negative pressure in water. A lot of times we think that negative pressure is not physically possible, which is true in a gas, but in a liquid or a solid, you can have negative pressure, and it's analogous to putting that material under tension. So here's an example of water in a vessel with a piston, and if you pull up on the piston, you'll be stretching those water molecules, putting them under tension, and they'll have a pressure that's negative relative to its environment. Now, how might we have negative pressure in water droplets? Our hypothesis is that the negative pressure could come from Laplace pressure, which makes sense with the experiments because Laplace pressure arises from surface curvature, from the curvature of the water droplet surface. So we're most familiar with positive Laplace pressure if you have a really small water droplet. This is responsible for the Kelvin effect, for example, where a really small droplet has a higher vapor pressure and evaporates more easily. So this is the equation for the Laplace pressure in a droplet with a radius of curvature r, and sigma is the surface tension of water. So the higher the radius of curvature, or the smaller the droplet, the larger the Laplace pressure is inside your droplet. You can also have negative Laplace pressure, where in this case you're kind of looking at a bubble in the water, and the surface tension wants to close that bubble, so therefore you're pulling on these water molecules, and it's associated with negative Laplace pressure, which uses the same equation just with negative radius of curvature. And this happens quite often in nature. It happens in tree xylem, on the leaf stomata. It happens in capillary bridges and in small pores. And here's an example of a water capillary bridge. So you have a water droplet sandwiched between two surfaces, sort of like a microscope slide. And this negative curvature of the droplet surface causes negative pressure within the water droplet. And that's also why it's really hard to pull microscope slides apart. So we want to know if negative pressure in water will increase the nucleation rate. So we decided to use molecular dynamics simulations to look at this because it's difficult to put water under tension in a lab experiment and also to measure where the ice forms. But in a simulation, in a molecular dynamic simulation, we can control all the thermodynamic properties of the water and observe where the ice forms. So here's just some brief background on molecular dynamic simulations. We have a box filled with water molecules, and each H2O molecule is represented by one of these cyan spheres, and they all interact with each other through this three-body potential, where each water molecule interacts with every other pair of two water molecules in the box, and the simulation computes the angle between each set of three water molecules, and it has a minimum potential when this angle matches the hydrogen bond angle of water. So that's what gives the water its hydrogen structure, even though they're spheres. To simulate heterogeneous freezing, we insert these brown spheres, which are acting as a substrate for ice to form on. And it's not modeling any specific substrate in nature, it's just a substrate on which the ice can form, so it freezes heterogeneously. These boxes have periodic boundary conditions, meaning that if a droplet moves outside of this wall, it'll re-enter the box from the other side. So it's sort of like an infinite box of water. And we use LAMPS, is the molecular dynamics simulation software. It's open source and developed by Sandia National Lab. And at each time step in the simulation, each water molecule it'll look at all of the molecules around it and compute the force on the molecule. And each time step calculates Newton's second law and will then move each water molecule according to the forces that are acting on it, and will change their velocity as well. So in order to measure the nucleation rate, we set up a whole bunch of identical boxes of water, and then we cool them all down at a constant cooling rate. So you can see the temperature decreasing here, and each box of water freezes at a slightly different temperature. And here's the same for the heterogeneous freezing cases. So then we can look at the number of times a water box froze with temperature as we cooled the simulation. So temperature is here on the x-axis, number of freezing events on the y-axis. And we can set those boxes to be whatever pressure we would like. So we first set them all to be 1 atmosphere, and then we put the water under tension, so they're at -500 atmospheres. And then we set the box to -1000 atmosphere. And we can already see that the boxes, as we cool from left to right, they start to freeze at warmer temperatures the more tension that the water is placed under. So we're already seeing that the negative pressure increases the freezing temperature. So what our simulations showed is that you can increase the ice nucleation rate without lowering the temperature if you have negative pressure. So here we have pressure and temperature coordinates, and the contours are showing lines of constant ice nucleation rate. So, for example, if we look at this pentagon data point, it means that at 0 atmosphere, or roughly 1 atmosphere, and at 235 Kelvin, the water has a nucleation rate of 10 to the 24 nucleation events per unit volume per unit time. So usually if we wanted to increase the nucleation rate, we would decrease the temperature, and then we would have a 3 orders of magnitude increase in the nucleation rate. But we could also stay at the same temperature and decrease the pressure instead, and we will reach the same magnitude of increase in the nucleation rate. So we wanted to see if we can put some, write some equations for this trend. So we used the pressure-dependent nucleation rate that I showed earlier, and you set them equal to each other at 2 points along this curve. And then you solve for the slope of these contours, delta T over delta P. So we can get a sense of the temperature-pressure relation for ice nucleation rate. And the slope is roughly linear. We've approximated it as linear in this pressure range. And it's dependent on the melting point, the volume difference between liquid and water, and the latent heat release. And this figure just shows that, again, in pressure-temperature coordinates, for both homogeneous and heterogeneous freezing, we see the same increase in freezing temperature with negative pressure. Lastly, because in all those simulations we told the box what pressure it was going to be at, we just wanted to verify that Laplace pressure, which is caused just from the droplet surface curvature, will still increase the nucleation rate in the way that we're expecting. So we set up this water capillary bridge. It's periodic, so this water is actually sandwiched between 2 of these substrates. And this is the expected Laplace pressure inside this geometry, where theta is the contact angle with the substrate, sigma is the surface tension of water, and h is the height of the capillary bridge. So we put this expected Laplace pressure into our expression, and this tells us that we should have the freezing temperature in this capillary should increase linearly with 1 over the capillary height, as all of these variables are constants. So this did turn out to be the case for different capillary heights. The freezing temperature increased linearly with 1 over the height of the capillary. So for our 24 angstrom tall capillary, we expect that it has a Laplace pressure of around minus 350 atmosphere, and the freezing temperature is roughly 4 Kelvin warmer than in the no surface curvature case. The red data point is an outlier because our capillary height was just getting so small that there were starting to be other factors influencing the ice nucleation rate just due to the water molecules being so tightly confined to such a small space. So we can't contribute the increase in freezing temperature to the Laplace pressure alone. There's other things happening there. So lastly, there's still a lot of work to know if this pressure idea plays any role in the atmosphere, and if so, how significant is it? But I wanted to just give some ideas on what the possible implications could be in the atmosphere. So first, consider we have a supercooled droplet in the atmosphere at minus 15 C, and it contains an IN, an ice nucleating particle inside of it, so that droplet would freeze within 1 second. If that water droplet, for whatever reason, maybe due to Laplace pressure or any mechanism, were to have a tension within the water of minus 500 atmospheres, then the droplet would freeze on that IN at minus 11 C instead. So for looking at IN in the atmosphere, we often look at these types of figures where temperature is on the x-axis and then like the concentration of active IN is on the y-axis. So here I've sort of drawn a rough line through the data points. So if we look at minus 11C, there would be a very low concentration of IMP active. But if, hypothetically, those water droplets were experiencing some negative pressure or tension, if it were on the order of minus 500 atmosphere negative pressure, then those would all be active at roughly 4 Celsius warmer. And you would instead, at minus 11, have one or two orders of magnitude more IN active at that temperature. Okay, so now I'm going to change topics very abruptly. We now have some new hypotheses about why supercooled droplets might freeze on impact with each other or when they're breaking up in the atmosphere. Maybe their surfaces are experiencing curvature, which is imposing Laplace pressure. So now let's look for some large droplets in clouds. And I'm going to turn to the spicule data set that was collected on this NCAR Gulfstream 5 aircraft. So Paul Lawson also gave a talk a few seminars ago regarding the spicule field campaign, for those of you who attended that. He was sharing data from the SPEC Learjet that flew at the cloud tops, and I will be showing some preliminary analysis of the data from the G5 that flew near the cloud base. And from all of the flights during the campaign, I selected 10 cloud regions that were well sampled below and in the cloud, and I thought they would make good candidates to study. So these are just showing the location of those 10 regions. And I couldn't have looked at all this data without the folks at RAF's Research, Science, and Instrumentation Group, RSIG. They really helped me make sense of and understand all the nuances of the in-situ data. So the cloud sampling strategy was we would fly just below the cloud base to measure what aerosols are going up into the cloud, and this also allowed me to know what the cloud base height was. Then we would fly the aircraft at various heights within the cloud. And I wanted to thank Colin because I used his flight notes also to verify the cloud base height. So for this study, I selected only flight tracks where we were passing through an updraft larger than 3 meters per second. And these are 2 examples from 2 of those regions that I showed, where the mesh line shows the cloud base height, and these lines show flight track segments that were in updraft. And for the rest of this analysis, I'm only using data from these tracks and not any other parts of the cloud. And then the data points show where we collected a GNI sample of, that's the giant nuclei impactor, and I'll explain more about that instrument later. So why did I only select updrafts? Just to start my analysis, I wanted to target moist adiabatic cloud parcels. So I wanted to make sure that the cloud was in the development stage, and that to make things a bit less complicated, to make sure that it was unmixed updraft core and with no entrained air from outside the cloud. So all my data analysis is in those regions of the cloud. And in such a moist adiabatic cloud parcel, there is a conserved quantity called the moist static energy. And it's conserved at all levels in the cloud if it's having moist adiabatic ascent. So the terms that go into the moist static energy are the thermal energy of the cloud parcel, the gravitational potential energy of the cloud parcel. So the thermal energy will decrease with height as the temperature decreases. Gravitational potential will increase with height in the cloud. And this term is latent heat release from phase changes in the cloud parcel, which will decrease with height in the cloud. So the reason why this variable is conserved is because energy gets transferred between these three different types of energy as the cloud parcel rises. And I just wanted to point out the variable definitions here, but also that these three, temperature, altitude, and saturation vapor pressure, are all variables that we can get from the in-situ cloud measurement. So I wanted to verify that the moist static energy was indeed a conserved quantity at the different levels in the cloud. And again, these are only looking at passes through an updraft. And so these are all the different regions that I looked at and different levels above the cloud base, starting with the measurements at the cloud base or just below the cloud base. And the moist static energy is pretty conserved throughout the height in the cloud for all of these regions. So this tells me that by selecting those updraft regions, I am more or less looking at a moist adiabatic parcel throughout the cloud. And yeah, wanted to thank also another person at RSIG who helped me with the water vapor data below the cloud base. Thank you, Stuart. So, so the next step for my analysis was to group all of these different cloud passes by similar water content. So since the moist static energy is conserved throughout the cloud, the value at the base should be the same as any value at any level in the cloud, so that this expression should hold true with values at the cloud base. And the change in saturation vapor pressure, above cloud base is actually the same as the liquid water content, or it's inversely related to the liquid water content at that height. So if I group my cloud passes into making sure they have the same liquid water content, then if the cloud passes at a greater height within the cloud, then the temperature above the cloud base will be smaller. But if it's at a lower height above the cloud base, then this temperature will be, the temperature difference between that cloud pass and cloud base will be larger. So that tells me that delta T, temperature from the cloud base, and delta Z, the height above cloud base, should be inversely related if I'm looking at a set of passes with the same liquid water content. So here I'm just showing the different liquid water content bins that I divided all of my cloud passes into, and I've plotted the correlation coefficient between the delta T and delta Z. So for all of the different liquid water content bins, there is a high anti-correlation between those values. So this is sort of just a sanity check to make sure that when I group my cloud passes by equal liquid water content, that they're still making sense and are having moist adiabatic properties. So the goal behind this is so that I can have groups of cloud passes that I can intercompare with each other for their largest droplet size. Because if I have a group of cloud passes with the same liquid water content, they've all condensed the same amount of water, but their droplet sizes may be different depending on the other properties of the cloud. So that's the aim here, and there was around 6 to 8 cloud passes in each of these liquid water content bins. So now that I've grouped these cloud passes into groups that can be compared against each other, let's see if we can learn anything about the droplet growth bottleneck that I mentioned at the beginning of the talk. There's 2 predominant theories for how water droplets might grow past this bottleneck. The The first is that they condense onto giant cloud nuclei, so they sort of get a head start in growing to a large droplet. The second is that entrainment of outside air and turbulent mixing helps broaden the size distributions. Since I'm looking only at unmixed cloud parcels, I won't be able to address this one at this time. But I can use the holodeck probe to identify the largest cloud droplet sizes in each of my cloud passes, and I can use the giant nuclei impactor to identify large condensation nuclei below the cloud base. So this is the AT.the giant nuclei impactor, and it was designed by Jorgen Jensen, and Josh Karnas helped me use this instrument as well during the speculum field campaign. So this is looking down into the instrument. There's a carousel of slides that are sort of like microscope slides, and when you press a button, it will eject one of the microscope slides out of this tube in the bottom of the aircraft, and then whatever aerosols are there will impact onto the slide, and then it pulls the slide back up in and advances to the next slide so you can repeat this measurement. And then those slides get taken back to a lab where we can measure how many large salt aerosols were deposited onto those slides and what sizes they were. And this little map shows all of the GNI slides taken during spicule, and the size of the data points is the equivalent mass of salt on those slides in grams per liter, I believe. So it just kind of, it's nice, it shows that there's less salt as you move away from the Gulf. This is the holodeck probe, this probe here, and it has a laser beam that exits one arm of the probe and is collected on the other side and recorded by a camera. And you'll notice that there's no focusing of the beam down to focal point because since it's taking a hologram, there is no focal plane. So any particle that passes through this laser beam between the arms will be collected in the hologram as part of the sample volume. So it records one hologram at a time, and within that hologram, we can apply some Fourier transforms to reconstruct which particles would have been in focus at different points along that optical axis between the arms. And if we do this at every value of z between the arms, we get a 3D distribution of the droplets. And I just want to quickly show a video of the software that's used to reconstruct it. So we're looking at one hologram. It's a PNG file. And then on this slider bar down here, where it says 66.5 millimeters, means that the software is reconstructing the hologram at 66.5 millimeters between the two probe arms. And when I play the video, the slider will start moving to different points along the optical axis, and you'll start to see which droplets come into focus. And when they're in focus, that's the Z position that they were at. So I'll start over. The big droplet comes into focus right about now. And then as we move along the Z-axis, you'll see different droplets come. You can wait for this one. This one comes into focus near the end. And there it is. So that's sort of what the holograms look like. Okay, so now we have a 3D distribution of the droplet sizes in the cloud. So I need to pick a quantitative metric to define the largest droplets in the cloud pass. So to do that, I selected, so here we're looking at the droplet sizes on the x-axis and the cumulative distribution function on the y-axis. So this line here shows at what point 10% of the droplets in this cloud pass were larger than this droplet size, and 90% of them were smaller than this droplet size. So we're at the 90% mark. So I selected the 90th percentile as the large droplet size. And the blue line here is from the CDP, and I found that when selecting the 90th percentile, CDP and holodeck, for the most part, agreed. But you can see the details of the distribution are different. So if you're interested in how the holodeck compares to the CDP, I'll be talking more about that at the RAL happy hour on Friday at 3:30. Okay, so now we have, for each cloud pass, what size were the largest droplets as defined by the 90th percentile. And we have aerosol information below the cloud, so I wanted to start making some preliminary comparisons for these 90th percentile sizes and other properties of the cloud. And just a reminder that they're grouped into cloud passes with the same liquid water content. So there were some results that we might have expected. Here we see that lower CN concentrations correspond to larger droplets in the cloud passes, which is what I expected. But there was also some groups of similar cloud passes with the same liquid water content, that had unexpected results. So here we're looking at CN concentration and the 90th percentile droplet size, and they're having the opposite trend of what one would have thought. Here's a comparison of the largest salt aerosol recorded below the cloud pass and the 90th percentile droplet size from the holodeck. So in some cases, the data is kind of scattered, so it's inconclusive or it's ambiguous. And then again, in some cases, for this liquid water content, this is sort of an unexpected result. It's the opposite trend than I would have thought, where you see larger salt aerosols, but smaller, larger salt aerosols, but smaller 90th percentile cloud droplets. So I would say that these preliminary results are just inconclusive at this point. Here's just kind of a summary for all the different liquid water content bins that I grouped them into. I performed a correlation between the 90th percentile droplet size and these various properties of the cloud. And on the y-axis is the correlation coefficient. So if it's 1, it's highly correlated. If it's -1, it's highly anti-correlated. And there's not really like a very consistent trend that pops out right away. So moving on to what I plan to do in the future, a lot of these questions of like what would the largest droplet size be based on the aerosol input, those lend themselves very well to a parcel model, or at least really require a parcel model to be involved in the analysis. But other questions like the mixing and entrainment aspect maybe can be addressed using the in-situ data, like providing more information than the parcel model might be able to tell us. So in the future, since in this preliminary analysis, I only looked at moist adiabatic conditions. I made sure they were moist adiabatic. In the future, I can look at cloud passes that show signs of mixing and entrainment and see if the droplet sizes show different trends in those regions. And furthermore, we can look at where in the clouds are the largest droplets found. Are they in the moist adiabatic core that I just looked at, or are there even larger droplets on the edges of the cloud in the mixed region? So, some future work for this data set. And lastly, to close out the talk, I wanted to bring the ice and the droplets together with the holodeck data with a small case study from the Escape Field campaign, which also flew the holodeck. It actually flew a very similar instrumentation as spicule and had a similar sampling strategy, similar to cloud types, but it was located closer to the Gulf, like based in Houston. So here is shown a flight track through a cloud, and it was a mixed phase cloud at -10 Celsius. So we collected the holodeck data from that, and it contained both ice crystals and liquid water droplets in the same holograms. So I took all the ice crystals and classified them into different crystal habits, shown here. And now on the x-axis, we are plotting a time series as we pass through the cloud. And I've plotted the concentrations of each of those ice crystal habits with these shorter bars in the bar plot. The shaded colors in the background correspond to these different droplet size distributions of the liquid water in the cloud. So here, these light blue bars show the concentration of liquid droplets in each hologram as we go through the cloud. And then my colleague Nitin used an algorithm that he developed in this paper to determine which droplet size distributions the droplets in the cloud were exhibiting. So he found that throughout this cloud, the water droplets would adopt one of these 4 droplet size distributions. And the shading in the background shows you where in the cloud the droplets were having these different size distributions. So this is very preliminary data and not enough data to draw any firm conclusions from, but it does start to raise some interesting questions, and there's some patterns we can speculate on. For example, at the edges of the cloud, in the downdraft subsiding shells, so the blue and the purple regions, we have liquid water droplets with larger diameters than the regions in the center of the cloud. And there's also fewer ice concentrations in those regions. In the center of the cloud, the orange and the green segments, we have more ice particles, and the droplet size distributions have shifted towards smaller sizes. So that could be that the droplets are evaporating, or the ice particles are taking up vapor at expense of the liquid droplets, causing their diameters to shrink. Or maybe it was the largest droplets that froze, so that those large droplets left this distribution. Just some possible patterns from this data. And lastly, to bring it full circle, one more quote from Sarah Lance et al. 2011 paper, that while IN are clearly very important for ice formation in the cloud, ice formation appears to also be very strongly dependent on the liquid droplet size distribution, making that previous analysis, being able to look at the ice particles and the liquid droplet distributions within the same sample volume, a really exciting possibility for future mixed-phase cloud studies. So before I give my concluding remarks, I just wanted to thank a lot of the amazing folks here who helped with all of this. Here's my host, my ASP host, Sarah, Colin, who I showed some of his experiments. This is Jorgen and Josh, who I helped run the GNI instrument during Spicule. And I also wanted to thank Julie at RAF, who's been super supportive and helpful in making this visit as successful as possible. So my key takeaway points are, we are looking at why are large cloud droplets linked with high ice concentrations, and how do those droplets grow? My simulations found that negative pressure due to curvature of the droplet surface can increase the nucleation rate of the water. From the spicule data set, I found that moist static energy is conserved within the updrafts sampled at different heights in the cloud. And the preliminary data are at this point inconclusive about any correlations between the largest droplets and the aerosol properties within the updraft core. And lastly, the holodeck measurements can be used for future studies of mixed phase microphysics, being able to look at the ice crystal relationship with the liquid droplet size distribution. Thank you very much. That is my talk.
Thanks, Elise, for that very interesting and broad seminar. Interesting to hear the different topics combined. Reminder for those of you online, we do have Slido active now, so feel free to submit your online questions there. Lynn has submitted a quick reminder. Her rel happy hour talk on Friday is 3 to 4, not 3:30.
Good to know.
Do we have any questions in her?
I had a question regarding you focus on large salt aerosols, but with the GNI, as I understand, you can get kind of an interesting assortment of biological particles as well. And so I was curious if you looked at how the larger biological sort of particles floating around contribute at all, if you were focusing mostly on salt at this point.
Oh, yeah, I have not looked at that. Yeah, I was just looking at the salt, or I was looking at what was measured on the slide as the largest equivalent salt dry diameter. So, yeah, I'll have to learn more about the post-analysis of those slides to understand if that's differentiating between the salt and the biological aerosols. But yeah, I haven't looked at that yet.
If I can just make a comment about that GNI, the way it's always been analyzed typically is it is put in a humid chamber and any salt particles absorb water, form droplets, form round droplets, and then those round droplets are detected and measured. So there, typically there hasn't been any effort made to find irregular particles. So really it's only been looking at round particles, which would be salt particles.
Thank you.
Thanks, Drew. We also have a comment online from Jan Jensen. He says he's a pro in the GNI. I am not surprised that there is a disconnect between the largest GCCN size and the drop sizes. The GCCN are created by marine breaking waves. The smaller CCN are largely added to the air as the air moves in overland from terrestrial and anthropogenic sources, thus lack of correlation. So thanks for that insight, Jan. Any other questions from the room?
Great job, Elise. It was cool to hear a lot of the background, especially for the molecular simulations. I hadn't really seen that spelled out. That was really neat. I'm curious, I noticed that a lot of, or those experiments were at really, really cold temperatures. Have you explored more of the mixed phase range, and what are your insights there? I guess I don't know if I've thought about this long enough to have a suspicion of what would happen, but I wonder if at different temperatures you would have more or less sensitivity to the internal pressure of the droplets.
Yeah, that's a really good point. So the temperatures are so ridiculously cold because we're dealing with such a small sample size in the simulations. But if I were to speculate, so here's the contours of constant nucleation rate and pressure and temperature coordinates. And as we go towards warmer temperatures, they're compressing. However, the slopes are staying parallel. So at this point, my speculation is that at mixed phase temperatures, the slope of the amount of negative pressure you'll need to increase the nucleation rate will stay the same because these slopes seem to be staying parallel. So yeah, the slope is the same, but yeah, that's a good question. So they're compressing more. So if you decrease the pressure more, you might actually reach an even higher order of magnitude of, that's sort of my speculation from the current data in this temperature range, but I think, more follow-up, I wouldn't make any conclusions. But yeah, I think more follow-up would be needed to verify across all temperature ranges.
Okay, thanks. We can talk more too later because I have so many things going through my head, so thanks.
I think we all have a lot going through our head after that broad talk. Jan Jansen has a follow-up question. The negative Laplace pressures of 500 to 1,000 atmospheres seems high. Are there cases where such pressures are observed?
Yeah, I totally agree. So the largest negative Laplace pressure that I've seen measured in nature is in tree xylem, in tree xylem they've been measured to be hundreds of atmospheres of negative pressure. And then in soil, there are capillary bridges formed between grains of soil, and those are also estimated to be on the scale of hundreds of atmospheres. But yeah, it's hard to imagine situations reaching 500 to minus 1,000 atmospheres of negative pressure.
Well, wouldn't you expect a porous aerosol with pores on the scale of, you showed 20 or so angstroms? You could have lots of particles with surface features of that scale. And if they were only wetted at the surface level and you formed a pore, why wouldn't you expect that to be very common in partially wetted aerosol?
Yeah, I think that's, I guess, if pores on the IN are reaching scales of 30 angstroms, then you'll start to reach like 270 atmosphere. So, there is definitely a lower limit because, this 18 angstrom, it still has a really increased freezing temperature, but yeah. So, that's a good point as well. It's just, it's unverified whether these negative pressures are found in the atmosphere.
Right, we have an online applause and question from Gabriel. Is there any way to program for mechanical agitation in the molecular simulations?
Yeah. I think so, yeah. We tried setting up some different things. We tried setting up two droplets coming into contact with each other and forming a little bridge as they come into contact. But I think the difficulty might be time scales and size scales. So if you need to have a lot of water droplet or a lot of water molecules in your simulation, and the mechanical agitation needs to happen over a long period of time, then the molecular dynamics simulation will be really costly. That's the main thing. But that would be interesting to maybe set up some highly curved droplet surfaces and see if ice forms during the movement of the droplet. Yeah, I guess to clarify here, we are looking at cases of constant negative pressure, like the droplet is under negative pressure for an extended period of time. But in a lot of the experiments I showed where the droplet's wobbling or the droplet's breaking up, the moments that the droplet might have these curved surfaces could be really short. It's a transient negative pressure, so that complicates the question as well. So, thanks for that question.
Oh, I just forgot to ask, what are the time scales?
Oh yeah, so
these simulations at these high low pause pressures?
yeah, so we're cooling them. Let's see. These. We're cooling them at 1 Kelvin per, or 0.25 Kelvin per nanosecond. So we're looking at nanosecond timescales. Yeah, and that's also why the temperatures are so cold and the nucleation rates we're looking at are really high, because the nucleation rate has to be high enough that these are going to freeze within nanoseconds.
Just a comment, since we're at NCAR, you guys have really big computers. Instead of give us a duration or something.
Alright, if there's no more questions in the room, I think we're at the end of our seminar hour, so thank you all for attending, and Elise, thank you for that insightful talk. We look forward to hearing more about the instrument comparisons at the RAL Happy Hour on Friday, and we look forward to seeing what papers come out of this fun analysis. Thanks.
Yeah, thank you for this opportunity. It's been a fantastic ASP visit. So.